Alright, neutralization. What is heartburn? A lot of people think that heartburn has something to do with your heart, and that's not true. It actually has something to do with a malfunction of a sphincter. It's a little muscle here that's supposed to close up and seal off the top of your stomach so that when your stomach, the muscle itself, is churning and mixing up the food, it's not splashing back up into your esophagus. When it does that, it causes a burning sensation because this is very acidic, and even though your stomach is coated with mucus, you don't really feel it, but this is more sensitive. Your esophagus is more sensitive to it. So you will actually feel the splash up there, and you will feel that burn because it's interacting with the muscle and the tissue in your esophagus, which is not good. So as a result, people will take some sort of antacid, opposite of acids, and they're going to try to neutralize some of that HCl that's in your stomach. Now, if you mix the acid, imagine the HCl in your stomach, with some sort of base, your Rolaids, Tums, milk of magnesia, and so forth, what's going to happen is these H's are going to react with the OH's, and they're going to make water. Now, if you have perfectly even amounts, if you have 5 moles of these guys and you have 5 moles of these guys, then you make water. But what if you don't have 5 and 5? What if you have maybe 8 and 5? It's better, it's not as acidic, but it's still not perfectly neutral. But if we did match them up perfectly, we could end up with water, which is neutral, and that's over here in the equation. But then I also put a salt here. We're going to have leftovers because we're only taking the H from the acid. There's something else there. And we're going to take the OH from the base. There's something else there. Those leftovers, part from the acid, part from the base, combine to form salt. This is a stereotypical equation. I bet if you looked in any chemistry book under this section, you'll always see this equation. HCl, there's your acid. NaOH is your base. Take the H and the OH, put them together, get water. Here's the Na and the Cl, put them together, you get your salt. So there's your water and your salt, the reaction's neutralized. Here's sulfuric acid, take the H and the OH, bond them together, make water. Then you got leftovers, K and then SO4. Hopefully by now you remember potassium's +1, sulfate's -2, crisscross them, that 2 ends up down there, and we get potassium sulfate. That's one of your salts. Buffers. Buffers you should think of as basically a mop. Their job is to go around, it's a chemical, and it's going to absorb or bond to any extra H's or any extra OH's that are in the solution. Now, buffers, their job is to keep a pH constant within a nice tight range. If this is the range where the pH should be, and it starts getting out of that range because there's more OH's, it'll absorb those OH's. If it starts getting more acidic because there's more H's around, it'll absorb and mop up those H's, so it'll knock it back into that range that we want it to be in. So over here you see that it's going to absorb or bond to the OH. This one's going to bond to the H. So it's going to keep going back and forth until it can keep that pH in the right range. Blood, I mentioned blood earlier. Blood has to be within a 7.35 and a 7.45 range. If it starts getting outside that range, either too acidic or too basic, then the body's going to start doing things to get it back into that range. One of the nice things that we have going is a whole system in our blood that's going to mop up extra H's. For instance, you've got extra H's produced from lactic acid from exercising to extreme intensities. You've got these extra H's, they're going to be absorbed. You have extra carbon dioxide building up. It's going to be absorbed again by this buffer system, or mopped up by this buffer system. So what we're looking at here is picking up any OH's and picking up any H's. So we've got two things kind of working together depending on what it's already absorbed. If you've got H2CO3, that's going to react and pick up the OH's. If you already have all the OH's mopped up and it's in the right range, but now it's starting to get too acidic, then the flip side of this, the HCO3, is going to end up picking up those H's, and then it's going to produce that, and so forth. So it kind of keeps going back and forth and absorbs all the extra OHs and H's, so it can stay in a nice tight range, right around 7.4. Okay, acid rain. Now normally, rain is slightly acidic. If you see the pH of 5.6 here, it's in this range. And it varies, obviously, from area to area, but it should be in this range. It's okay if it's slightly acidic. And the reason that it happens is that it's reacting with the carbon dioxide in the atmosphere, and it's making carbonic acid. Here's your H's, and then here's your carbonate. So it's making carbonic acid, and that's a weak acid, and that's in the environment. There's nothing we're going to do about that. And that's going to make rain slightly acidic. Rain is not pure. It does have impurities in it, and one of the impurities right here is carbonic acid. So it's not going to be 7. It's going to be a little bit lower than that. Now this is not a problem because it is mild. Plants, animals, everything has adapted to it. It's when the pH gets lower than that that we start having problems. So for instance, if you're a car manufacturer, if you're creating a statue, if you're planting plants in a certain area, you need to know what the pH of the rain is that that area typically gets, so you could react accordingly. Take a look at this statue. This is how it should be. This is what it looks like after acid rain has started to wear it away. Take a look at where we are over here. Remember I said rain should be about 5.6. Look at all these values. 4.3s, 4.5s, 4.6s. Getting a little bit better as we move out here. Now we're in the 5s. We have some 5.6, 5.7, 6.4s. Again, back here to the 5s and stuff. So it's really the northeast that has issues. Maybe down the coast a little bit. But this is the lowest pH, or the most acidic pH. Now, one of the causes of acid rain are SOx and NOx. I know it sounds like a Dr. Seuss book, but this X is a variable. This could be SO2, sulfur dioxide. Could be SO3, sulfur trioxide, and so forth. So we end up putting these sulfur and nitrogen oxides up in the atmosphere. Now, it gets up there sometimes by nature. Volcanoes could be produced during different reactions in nature, but it's mostly due to humans. If humans weren't around, these levels would not be as high. We're screwing these things up. We're burning stuff, coal, oil, diesel, gasoline. Anytime you run your car, you're producing these pollutants, and they're going up in the environment, and they're reacting with the water in the atmosphere, and they're producing sulfuric acid and nitric acid, and then it's obviously combining with the water and falling as rain, and then we have these substances that are coming down that are harming nature. So what are some ways we could prevent acid rain other than just reducing emissions? Well, they have these scrubbers, devices that just can remove these SOx and NOx from power plant emissions before they leave the smokestack, so the smoke or the vapors that are leaving are a little bit cleaner than they normally are. Catalytic converters, they're now in the vehicles, and their job is to clean up the emissions before it enters the atmosphere. And then we could also take the diesel fuel and remove the sulfur even before we burn it. If you take some or all the sulfur out, you're going to produce less SOx in the atmosphere, and it's going to produce less of this sulfuric acid. So there are some things that we can do, and obviously technology is improving at ridiculous rates, and they're making progress, but it could be sped up and reduce this problem of acid rain. Okay, that's it for the notes. Good luck.